In the previous video, we talked about expanding binomials and Pascal's triangle. In this video, I want to tie that in a little bit more closely to the binomial theorem. And I have a copy of Pascal's triangle right here, and I also want to bring back in an idea that we talked about 2 videos back, which is a combination and factorials. So a couple of things I want to point out here. For starters, the Pascal's triangle I've constructed here is for powers of n. So n equals 0, n equals 1 is the second row, n equals 2 is the third, and 3, and 4, and 5, and 6, and so on. And remember, you can get each entry by adding the 2 numbers above and diagonal to the next entry. So 1 plus 5 is 6 is how we get that entry. And 5 plus 10 is 15 is how we get the next entry. And we always have 1s along the outsides. So tying this into combinations, a couple of combinations I want to talk about. I want to talk about first 6 choose 0. Now don't forget a couple of things from previous video. Combination n choose j is given by the formula n factorial divided by j factorial times n minus j factorial. And we're also going to need that 0 factorial is defined to be 1. Okay, so 6 choose 0 is 6 factorial over 0 factorial times 6 minus 0 factorial, which is 6 factorial over 1 times 6 factorial. Ooh, that's nice. I don't know what 6 factorial is, but it definitely cancels with the 6 factorial in the denominator. Okay, cool. Okay, bear with me. Let me try a couple more. Let's do 6 choose 1. So 6 choose 1 is 6 factorial over 1 factorial, and then 6 minus 1 factorial. So that's 6 factorial over 1 factorial is 1, and that would be 5 factorial. So we spent a lot of time in the previous video reducing factorials, and remember this is 6 times 5 times 4 times 3 times 2 times 1. And then 5 factorial is 5, 4, 3, 2, 1. So that's going to cancel, leaving us with just 6. Okay. Okay. I'm going to do 2 more. 6 choose 2. 6 factorial over 2 factorial times 6 minus 2 factorial. So 6 factorial over 2 factorial times 4 factorial. Okay, so just like the canceling that happened in the previous one, the 4 factorial is going to totally cancel away with much of the 6 factorial, leaving us with 6 times 5 in the numerator. So we'll have 6 times 5 over 2 times 1. 30 divided by 2 is 15. These entries should look very familiar to you. Whoops, 1, 6, 15, 1, 6, 15. These entries, 6 choose 0, 6 choose 1, 6 choose 2, are giving us the Pascal's triangle entry. 6 choose 0, 6 choose 1, 6 choose 2. I bet 6 choose 3 is going to be 20. Okay, let's test it out because this will be our last one. 6 choose 3. 6 factorial over 3 factorial times 6 minus 3 factorial. So 6 factorial over 3 factorial times 3 factorial. So one of those 3 factorials will cancel away, leaving us 6 times 5 times 4 in the top. And so we've got 6 times 5 times 4 over 3 times 2 times 1. So let's see. Oh, 3 times 2 is 6. That gives us, 5 times 4, 20. Aha. So each of these factorials, or combinations I should say, gives us the entries in Pascal's triangle. In fact, a lot of times you see Pascal's triangle written like this. So due to space, I only wrote out the first n equals 0 to n equals 4, but each of these entries here, 4 choose 0 gives us 1 if we used our formula. And 4 choose 1 should give us 4. And 4 choose 2 should give us 6. So in some cases, you'll see Pascal's triangle written in this combinations method instead. And just like in the expansion video that we did a few minutes ago, these entries will give us the coefficients of expanding out a polynomial. So let's kind of tie this all together. So let's find the fourth term for a plus b to the fifth. Now I know we did one just like this in the previous video, but bear with me. So in the previous video, we didn't have Pascal's triangle written in this format. We had 1, 5, 10, 10, 5, 1 instead. And we went we went, let's see, a to the fifth, b to the 0, a to the fourth, b to the 1, a to the third, b to the 2, a to the 2, b to the third, a to the 1, b to the fourth, and finally 1b to the fifth. And we had addition signs everywhere. Okay, nothing has changed. It's just instead of writing those as Pascal's triangle entries, we're going to write them with their combinations format. There we go. So instead of 1, 5, 10, 10, 5, 1, I'm just writing 5 choose 0, 5 choose 1, 5 choose 2, and so on, because those give me all the same values. Okay, here's an important part of this. We want to find the fourth term. Now, I don't mean to insult your intelligence with how to count, but this is the first term, second term, third term. Here's our fourth term. What frequently confuses people is the fourth term does not have any 4s in it. So they want the fourth term to be a to the 4 or b to the 4. But since we're starting with the first term, starting at 0 b's and 5 a's, then the first term is 5 choose 0. The second, third, fourth term is 5 choose 3. But there is a cool pattern here. Notice every single time the exponent on the b matches the j version of our combination. Cool. So to find the fourth term, we are looking at the term that has one less exponent on our b's. So fourth term has b to the 3. And the reason I'm looking at the b's is because it's 5 choose 3. So the fourth term would have 5 choose 3. The exponent on the b would match, and now I have to make my exponents add up to 5, so it must be a to the 2. Okay, so that will be 5 factorial over 3 factorial. 5 minus 3 is 2 factorial. A squared b cubed. Remember, that's going to cancel a whole bunch. That whole 3 factorial is going to leave a 5 times a 4 in the numerator. So we have 20 over 2 factorial, which is 2, a squared b cubed, which is 10, a squared b cubed. Cool. Okay, let's make these gradually harder. Before I do the next difficult one, I want to point this out. The fourth term has b to the 3, one less. And the reason I focus on that is because that is the j in the 5 choose j. So 5 choose 3. And then I make sure that my exponents add up to n. So if this is a 3, that must be a 2. Okay, let's make it a little bit harder. Okay, so let's find the fourth term for x plus 2 to the fifth. So since we kept our n the same as the previous example, we're still using this row from our Pascal's Triangle binomial theorem. And I took away the row of the expansion. So let's do this way. This would be the fourth term would be choose 3. It's always going to be one less. And then the n is 5, whatever the exponent is. I want to say A and B needs to match the J, and then this needs to make it add up to 5, but I don't have an A and a B, so I'm going to say 5 choose 3 x squared and 2 to the third, because A in this problem is the x and B is the 2. Okay, we already figured out that 5 choose 3 is 10 x squared, and 2 cubed is 8, so 80 x squared would be our answer. Okay, let's make it a little bit more challenging. All right, now let's find the fifth term of 3x minus 2 to the fifth power. Okay, so I know my n is 5 because that's the exponent. If I'm finding the fifth term, it's going to be 5 choose 4. And I'd love to say b to the 4, so a has to be to the 1. But in this problem, a is being represented by 3x and b is negative 2. So we've got 3x to the 1 and negative 2 to the 4th. So 5 choose 4 is 5 factorial over 4 factorial times 5 minus 4 factorial. 3x, negative 2 to the 4th is positive 16. Okay, so 5 minus 4 factorial is 1 factorial. So this is just a 1. And the 5 factorial on the top cancels with the 4 factorial on the bottom, leaving just 5. So we've got 5 times 3 times 16, which is 240, and x. Okay, let's do 2 more. Let's find the 7th term of x plus 2 to the 10th power. Now, not only would I not want to FOIL that out, I don't even feel like writing out the Pascal's triangle up to n equals 10. So this is a much faster way if we just have to find one term. So the n we're going to use is 10. Since we're finding the 7th term, it's going to be 10 choose 6. I would like to have a and b so that b is going to be to the 6th. They have to add up to 10. That means a has to be to the 4th. So this would be 10 choose 6. A is x. B is 2. 10 choose 6 works out to be, let's see, 10 factorial over 6 factorial. 10 minus 6 is 4 factorial. 2 to the 6th is 64. And when we get to reducing these, the 6 cancels with much of the factorial. 10, 9, 8, up to 7 is left. 4 is 4, 3, 2, 1. And there's a lot of canceling even that happens further. 4 and 2 make 8. And 3 goes into 9 3 times. So if your calculator doesn't do 10 choose 6 for you, there are a lot of easy simplifications here that you don't have to use a big calculator for. So 3 times 7 is 21, times 10 is 210, x to the 4th times 64. And when we multiply those together, we get 13,440 x to the 4th. All right, one more. Okay, let's find the 13th term of 2x squared minus y to the 15th power. Again, a little bit too big of an n for a Pascal's triangle, so we're going to have n is 15. Since it's the 13th term, choose 12. Okay, I would like to have b be 12. They have to add up to 15, so a must be 3. So this will be 15, choose 12. A is 2x squared in this problem, and b is negative y. Okay, let's see. Let me go over here and do this. 15 factorial, 12 factorial, and 3 factorial from 15 minus 12. The 12 factorial totally cancels, leaving 15, 14, 13. And 3 is 3 times 2 times 1. So let's see, canceling even more, 3 goes into 15 5 times, 2 goes into 14 7 times, and I still need my calculator, but 5 times 7 times 13 is much nicer than 15 times 14 times 13. So what we're left with there is 455. Okay, for the a cubed, 2 cubed is 8. X to the 2 to the 3 is x to the 6th. And for that negative y, negative 1 to an even exponent of 12 is positive, so y to the 12th. Only thing left to do is 455 times 8. That is 3,640 x to the 6th, y to the 12th. Awesome.